Okay, so let me remind you where we left off yesterday morning. So first I'll write down the most of the full equation that we derived. So the equation was of this form for the intermediate scattering function. Actually, let me use Q for the reason that I said before. Thank you. And the memory function had the form and living inside this, what we call the vertex, this coupling constant, were things like the density and S of k. So simple either thermodynamic or structural information that we could plug in and solve the equation to get solutions. And to remind you about what the solutions looked like, some of the properties, there is a critical point, Tc, and the behavior of the relaxation time approaching Tc looks like, and I'll tell you what the constant gamma is in a second. There's also a hierarchy of relaxation times, or of relaxation behavior, so that there is the appearance of a plateau and the decay from the plateau. And as one approaches the transition from above, the plateau lives longer and longer. The behavior as you decay, so this defines a plateau height, which in the full theory is dependent on the wave vector. And the decay into the plateau has this form. And the decay from the plateau has this form. And there's a relationship between the A and B. So there's a lot of detailed information. Where this is a gamma function. That's the relationship between A and B. And gamma is related to A and B. The terminal relaxation is stretched exponential, but we're not going to talk about that. So these are the main properties of the theory. And then we said that if you just sort of ignore all the wave vector and you want to get the sort of gross mathematical form that's relevant for, see, I've already used very poor board technique because this is actually the board that doesn't slide up, so you can't see. So I'll just move over here. So this is still here. If you just wiped away all the wave vector dependence, you would get an equation just for the typical function, something of this form. And aside from the details like a wave vector dependent plateau and the fact that there's stretched exponential relaxation, all the same behavior is obtained from this kind of equation. So very, very quickly, we went through the things that actually works. A lot of this phenomenology you can see, let's say, in experiments or computer simulation, but only over a very narrow range of the earliest phases of supercooling. So something like 3 decades, 4 decades of supercooling, right below the onset of glassy behavior, you can fit your data to this, and this gives you a good description of gross behavior. And in particular, some of these things are in very detail successfully recovered. So for example, the k-dependence of the plateau is really very remarkably verified in computer simulation, for example. But of course, eventually, this power law fit is not going to work. And you can keep supercooling well past where the theory would say there's a TC. So that's one. Either you would view this as a failure of the theory, or it actually means it's not a failure of the theory, it's that the theory is not supposed to get the behavior there, and that's what we're going to talk about in 5 minutes or so, which of these are right. One other thing I didn't mention last lecture is there are a few other things that start happening already in the regime where this grossly fits the dynamical behavior that you can observe that you can't successfully get from MCT. So for example, you start to see violation of the Stokes Einstein relation. And I don't know if Mark Ediger talked about this, but for example, if you measure the diffusion constant and you multiply by the relaxation time, grossly, that might fit something like this. If gamma is equal, or let's use a different exponent. If alpha is 0, that's something like the Stokes Einstein relation. But what you start to see is that alpha is not 0. And so there's basically a decoupling between diffusive behavior, which let's say is dominated by the particles that are moving fastest, the few particles that are moving fastest, and the relaxation time, which is dominated by the 95% of particles at any given time that are relaxing slowly. Mode coupling theory predicts, if anything, a very, very weak version of this. And so, and this starts to get violated much more strongly already in the regime where mode coupling theory is supposed to work. So that presumably this is related to dynamical heterogeneity of sort of localized jump-like motion that you've seen, I think, in simulations, and it's been talked about in experiments. So there will be sort of bursts of activity that are locally correlated, and as we'll talk about at the end, that's not something that this kind of theory should get right, and it doesn't. And another related example of this is if you look at the non-Gaussian parameter, which is, I can't remember if this is right. Yeah, it's 4, right? T5. Right, so if you have a purely Gaussian theory, this should be 0. But if you plot this in your simulation, you start to see a peak, and the peak grows. And so there is some time scale which is actually associated with leaving the plateau. It's not the alpha relaxation time, but it's this time scale where this thing peaks. And that's also associated with these bursts of local activity of motion where particles are moving much more than you would typically expect from the particle displacement distribution. So if you calculate this might reach order 1 or higher in a Lennard-Jones simulation, but if you calculate this within MCT, and it's not clear how you do that, but there's an equivalent way to get single particle displacement properties, you find things that are much, much smaller, like 0.1. So this is not described properly. Okay? So then the point that we made, and this is where then the new stuff will start, is that this equation actually can be obtained from a model for which essentially it's exact. Right? And you've learned about this, I think, in various different sets of lectures. So these are the class of mean field spin glass models. The only difference is that it's natural in the models that this is a first derivative, but you should take my word for it that it doesn't matter with respect to the behavior of the slow dynamics. So you can replace the second derivative with the first derivative. Okay? So what are those models? They would be models like, I think, Leticia mentioned. Right? So this would be the Hamiltonian, where these are, let's say, continuous variables, and then you would have, this is all-to-all connected degrees of freedom. So the mean of J is 0, right? And the square of J is something like 1 over n squared, I guess. So, and you can just generalize these to more than 3, 4, 5, 6, however many you want. And if you have a Langevin dynamics for this with a white noise, so you will have an equation of motion for your field, and you have the spherical constraint that Leticia talked about, which is enforced by this Lagrange multiplier or mass term. Then let's see. And the noise correlator would be something like so if you solve the equation, it turns out because of the statistical properties of J, if you, for example, even if you wrote out a diagrammatic approach to expanding this, only the terms that give this equation survive. So the exact equation of motion is going to be basically that schematic equation I wrote for you. All the other diagrams that look like they have, in diagrammatic terms, vertex corrections vanish with higher powers of 1 over n compared to all of the mode coupling diagrams or the self-consistent Born diagrams. So you just get that simple structure back. And this is exact in the model. And I think Francesco mentioned Reichman yesterday. So as far as I understand, constructing these models actually also took motivation from work in turbulence from the late 50s. And there, Reichman was interested in understanding the Navier-Stokes equation and looking at the energy spectrum. And basically, the Navier-Stokes equation is very hard to solve. So he took a random coupling version of the Navier-Stokes equation, which actually breaks Galilean invariance. So, but in that model, he could solve the problem exactly, and you get exactly something like this, and you get a slightly different energy spectrum than the right one. Instead of a 5/3 power, you get a 3/2 power. Those are very, very close, and the difference comes from the breaking of the random. You now have random Galilean invariance instead of Galilean invariance. But no matter, that's not important to us. That was the motivation for making models like this. Construct a model for which diagrammatically you already know that the exact solution is going to be the equation you want. But of course, that comes with great benefits, because this kind of model, as we've learned from the people who know it much better than I do, has a whole, cornucopia of properties for which you could then start to think, well, this is, in the high temperature or above the transition, this kind of equation for the model tells us what the dynamics should be coming from above the glass transition. Okay, the transition that you see, which I call TC here, but Francesco called TD for dynamical, is a purely dynamical transition in the model. Right? There's no signature in the thermodynamics of any change, but or in the thermodynamics that you can really measure easily. Okay, and then the system basically, as Francesco said yesterday, above the transition, it's like you have one cluster, and then below the transition, the free energy of the system will break into disconnected clusters, and so you will have a non-trivial configurational entropy. And then as you continue to cool the system down, you will actually lose extensivity. You'll just have a few of these states, and that's the Kautzmann transition in the model. So then you could start to think in a much more global sense. This kind of theory shouldn't work at very low temperatures. It should work over, let's say, the first few decades of supercooling, and there should be, in non-mean field, the remnant of this dynamical transition, which might get avoided because you're in low space dimensions, like 3 space dimensions. And then the behavior below that temperature will be related to, let's say, hopping between these clusters or some activated processes. Okay, and then eventually you'll run out of activated clusters, clusters that you can hop to, and the system is basically stuck in an ideal glass sense. And you could debate whether or not in low space dimensions that really exists or not. Okay, so in that sense, you really might view this kind of equation as coming from the detailed liquid state version of what should be a mean field theory. And of course, some of the approximations we used are mean field-like. I mean, we used an uncontrolled factorization of a 4-point density correlation function into product of 2-point density correlation functions, and that also has the flavor of all the kinds of mean field theories, the crudest ones that you learn in lots of different subjects. So the question is that the right way to think about this? And so that's what I want to talk about for the next. Yes. Mm-hmm. Yes. Sure. Yeah. Yeah. Mm-hmm. So, I mean, you could really ask if, this doesn't look like a realistic particle model. So how much should I believe the fact that I constructed a model that has an equation for its correlation function that looks like this one? I mean, you could actually try to work harder and start with microscopic considerations and try to justify things that look like this. And there's some success in doing that as well. So what's the motivation for this? Well, you could think I could construct something like a free energy functional for the system that might have some non-quadratic component to it. And by the way, as I mentioned, you can take any number, p equals 3 or more works. The only difference that you find is this becomes so in that sense you could view this as some sort of associated with some sort of free energy expansion in the density, right? And that the randomness is something that you're putting in either through thermodynamic considerations like replica considerations, or it's just a proxy for self-generated disorder that you're trying to make the analogy. But I agree that it's a little bit tenuous, and that's one of the points that I'm going to try to emphasize, that it's not at all clear that this should be viewed as even the right liquid state mean field theory. Another way you might want to ask the question is, and this is what we're going to address for the next 40 minutes or so, is if I looked at a real liquid in higher space dimensions, is this right? Are the predictions of this right? So that's a property you would want your mean field theory to have, that at least as d goes to infinity, you understand what's going on. Mm-hmm. Does the density fluctuate a lot? I'm not sure I know how to answer that question, because I mean there's a lot of ways you could think about what you mean by the density. But what certainly does have growing fluctuations are things related to this order parameter. So maybe you've learned in this school about chi4. So chi4 is really, if you think about some sort of order parameter like this, which is really just a superposition of FKTs, right? If I Fourier transform this, then, and I'll call this, I'll call this F. Then the fluctuations of F grow. So you do have growing fluctuations in something like this. Okay, and we'll come back to this. And in fact, actually, that's something I should have mentioned. One of the non-trivial things about these models is actually the equivalent of that 4-point function that I just sketched actually diverges at TD or TC. Okay? So there is a diverging dynamical length scale in the model. So even though these properties of local dynamic heterogeneity don't seem to be described well, which are, you know, in a sense more related to activated processes that might already exist in low space dimensions and invade the system above TD, and therefore these ways of thinking about the problem doesn't contain that physics at all. There is something else going on, which is that there is some growing mean spatial correlation of the dynamics, which is non-trivial. And so in this model, chi4 actually diverges at the transition. And I'll show, hopefully, at the end of the lecture, there's a version of that in the true liquid state model, which has a diverging length scale as well, TD. And that's associated with the growing length scale of chi4. So that's the growing length scale associated with dynamical heterogeneity. Mm-hmm.
Quick question about the relaxation of FKT.
Mm-hmm.
If I look at the graph and look at the size of plateau, could I say like it was parameter without like I don't know the way of like making conclusions about TD or about TD?
Maybe the answer is yes, but in my zeroth order answer is no. That is qualitatively. But it's going to vary from system to system. So that's a quantitative measure. So the plateau lives for a decade or something like that. And I think in one system or another, that would be closer or less close to the transition. It might be similar to, you know, in silica versus Leonard-Jones mixtures or something like that. It's not going to be the same. Any other questions? One other thing that I wanted to mention, but I'm not going to talk about, is that there is also, I mean, this has maybe no relationship to the things that we're talking about at this meeting, but there are quantum versions of this kind of spin glass model where you replace these things by fermionic degrees of freedom. So you could have a model where you had something like okay, so the properties of the random coupling are identical to in the classical glass models. Okay, and actually these models were introduced by Sachdev and Ye in the early 90s, and then they have been further understood by Kitaev, so they're called SYK models. And the reason that people are interested in them has essentially nothing to do with, well, presumably nothing to do with what we're talking about here. So these are, let's say, Majorana fermions, but these could be raising and lowering operators for fermionic degrees of freedom. So this would be like a p equals 4 version of the model that we took if we had 4 of these guys. Okay, now if you work out by field theory the self-energy for these problems, they look exactly like mode coupling theory with p equals, in this case it would be p equals 4, so that would be like phi cubed. So the exact equations for the dynamical, for the Green's function look exactly like MCT. I mean, there are some differences that come from the fact that you have fermions and you have to respect the fermionic boundary conditions and imaginary time. But already that's kind of interesting. So the models were first introduced to think about disordered quantum spin systems and think about non-Fermi liquid behavior in those systems, and then they were sort of ignored. And then Kitaev sort of showed that these models have properties that seem to be related to properties of simple models of black holes. So for example, the model at 0 temperature has a finite entropy. And another property of the model is that in the strong coupling low temperature limit, there's certain kinds of invariances in the equations that are actually the same as the invariances of these mode coupling equations. And that's also shared by these black hole models. And there's another interesting property, which is if you compute a 4-point function, which is different than chi4. Actually, chi4 in this model also diverges, but it diverges at 0 temperature, which is important. But if you change the time ordering in your chi4, then you have a correlator that people call out of time ordered correlations. And out-of-time ordered correlations measure the chaotic behavior of a system, the mixing behavior of a system through the decay of that function. And you can sort of calculate something that's very related to the Lyapunov exponent of the model. And very recently, Juan Maldacena proved that there's an upper bound, that this decay constant of this 4-point function can never be greater than 2 pi over beta. And these models saturate the bound. And that's also true for these black hole models. So people feel somehow that these models are holographic dual models of a condensed matter system that are holographically dual to simple models of black holes. But as far as I understand, no one has proved that this is true. But there's been a flurry of activity. And my feeling is, and some work that I've been doing with Giulio Baroli and Jorge Kirchon would suggest that actually lots of those interesting properties are already embedded in what we understand about these models. So for example, it would appear that the dynamical transition in the model gets pushed to 0 temperature. Okay, and that's why the chi-4 diverges at 0 temperature. Okay, but it also suggests that the entropy that you see at 0 temperature is the configurational entropy that jumps at the dynamical transition. And that would be very interesting if this is true. We have lots of pieces of evidence that this is true, but we're not done, really being sure that this is the case. So that's another interesting aspect of these kinds of models that everything basically comes back at the end to something like this. So it's sort of amusing that when you look at the papers in condensed matter physics or high energy physics, the equations they're writing down are just the mode coupling equations with some constraints for the fact that there's quantum effects in the system, which is nice. Okay, so let's get back to reality and come back to the question that I wanted to address, which is how should we view this? Should we view this as sort of the fully microscopic k-dependent version of what emerges from these kinds of models? Okay, so one thing that you could do is you could just say, well, what should I expect to happen if I simulated a Lennard-Jones liquid or hard spheres in higher spatial dimensions? So you could do this, and you would expect that the properties that are found in this kind of theory are more and more easily observed in a convincing way. Right? As I said, some of these things are not very convincing. I mean, you do see two-step relaxation. You do see stretch exponential relaxation. For sure, you can fit relaxation times the power laws. But one thing that I urge you to do as an exercise is take an Arrhenius temperature dependence and fit it to a power law. Trust me, it fits beautifully over some range which is not really different than the range for which you can get this behavior, fit to fit, which is a cautionary tale of, you can believe what you want to believe when you look at data, but it doesn't mean it's real. And so what you would hope that you see if you simulate a system in higher spatial dimensions is things like this might be more observable. That is, you might start to see a suppression of this local hopping behavior. Right? You might see a wider window, let's say, where the violation of the Stokes Einstein relation goes away, or the non-Gaussian parameter is very small, even though you are seeing clearly glassy behavior. So there are two things that could happen, right? One thing could be, well, you go to higher dimensions and you just push to lower temperatures or higher densities where the onset of slow dynamics is. And then, of course, you're not going to see violations of the Stokes-Einstein relation or large non-Gaussian parameters, but there's no glassy behavior there. Or instead, you could see something non-trivial, which is non-Gaussian parameters get much smaller, violations of Stokes-Einstein start to go away, but you really do see real glassy behavior over a longer and longer range of times. Okay? So, would that be proof that this is the right way to think about liquids in the mean field sense? No. but it would be some sort of qualitative correspondence between expectations and what you would expect from these kinds of models. So people have done this. Actually, Joel Eves is sitting right there next to Ludovic. So he and I wrote a paper in 2009 where we simulated the Cobb-Anderson system in 4 spatial dimensions. And we saw this was very hard to do for a lot of reasons. One was you've got a non-trivial phase diagram of the system, and things shift. You know, there's temperature and density. And so things move around, and you want to make sure you're comparing apples to apples. And so this was hard to do, but once one controls for all these things, we saw anecdotally that it looked like Stokes Einstein violation was weaker and things like this. Okay, and then Patrick came along and did it much, much better than we did. And he was smarter in 2 ways. So one way he was smarter was he said, screw Leonard-Jones. Hard spheres are a much better system to ask this question in because I don't have to worry about temperature. I just have to worry about volume fraction. So I don't have to scale the points where I think this TC is, you know, in some weird phase diagram that's got temperature along one axis and density along another. I just have volume fraction, so I can just see where the onset of slow dynamics is, and you know, maybe that shifts with higher space dimension, maybe it doesn't. The second thing that he was very, very smart about, and this will come back as a theme in the next hour, is that Joel and I were very worried that in 4D you have to simulate a much bigger system than in 3D. If I want to simulate 1,000 particles in 3D, then I should probably simulate something like 10,000 particles in 4D. And actually what we will see is that, or I will discuss, is that dynamics become increasingly local in high space dimensions. And in fact, this is a theme in physics in general. So in strongly correlated materials, if you look at something called dynamical mean field theory, this is the correct infinite dimensional solution of the Hubbard model, and it's exactly local. So there's no wave vector dependence of the self-energy in the infinite dimensional solution. It's the exact solution. And in fact, I think Francesco is going to talk later today, maybe about, or tomorrow, about some properties of the static, I think, D equals infinity solution for classical fluids, and a lot of those themes come back. And actually, a lot of the diagrams that you draw that are the local diagrams are like the dynamical mean field theory diagrams. So Patrick was smart enough to know, well, if everything's local, I don't need, you know, for an 8-dimensional hard sphere simulation, I don't need, you know, 10 to the 8 particles, or at least I might not. Yes? Well, I'll come back to this in a second. So more local in terms of the dependence, let's say, on G of R, for example. Right? Just contact becomes important. And well, dynamics can be correlated over very long length scales, even if you just have second virial behavior. But that's a non-trivial thing, so we'll talk about that. So anyway, what happens when you do this? You see exactly what you would hope. So I think Francesco and Patrick have a paper from 2013 or so in JCP. I think Giorgio Parisi is on it. I can't remember all the authors. But they look at this question, let's say, of Stokes Einstein violation up to 8 or 10 dimensions, 8 in hard spheres. And you see exactly this. What happens is really beautiful. It's very non-trivial. You see basically that the FKT, and let's say you're measuring K at the peak of the structure factor versus log T, you know, really has the same kind of behavior, and you get this very, very strong plateau. But over a wider and wider window, let's say, which widens with increasing D, you have a regime where there's a strong plateau in the system, and the system is exhibiting clear glass-forming behavior, but things like the Stokes-Einstein violation are basically not observed at all. Okay, and if you keep going to longer times, then you see the onset of a hopping regime. So it looks like there's a window that's widening, that's opening in the system, where you can really clearly observe what you expect from a mean field theory over longer and longer timescales. This is really nice. And in fact, actually, there are even 3-dimensional systems that somewhat exhibit this kind of behavior. So you could take a potential, that's like this, and crank the density up. So this is called the Gaussian core model. And then effectively, there are long tails of the interaction potential. So a particle is effectively interacting with hundreds of particles, but it's in 3 dimensions. And this is also, you can make mean field models this way, like Katz models, where you have long-range spatial interactions. You see the same behavior. You see the non-Gaussian, you see exactly this, okay, where there is a really nice regime of sort of glass-forming, plateau formation behavior of the 2-point function. The non-Gaussian parameter is really suppressed, and the Stokes Einstein violation is almost non-existent. And you could ask the question, well, what does it look like? What are the particles doing? And Daniele Koslovich has looked at this, and you see really interesting things. You see far fewer of these local bursty kinds of motions. You just see long, sort of displacement fields where particles are displaced a small amount over very long length scales. So there's, and also the chi4, however, which we've talked about here, actually grows much more strongly in this system, in this Gaussian core model. So the peak gets enormously high, right? And this, again, this is related to what Ludovic was asking, but there are really long-range correlations in the system dynamically. Okay, so, and a very interesting question, which I don't think has been resolved, but it's something that, Akeda and Koslovich and I have tried to talk about. Are there metrics to ask the question for your favorite system, let's say the Lennard-Jones in 3D, how much of the growth of chi4 comes from dynamic heterogeneity that's already of this mean field variety, and how much of it is coming from this non-mean field-like activated processes of local particles bursting? There should be a way to quantify this in a way that's not qualitative. Because you do start to see, even in the 3-dimensional Lennard-Jones system, you start to see behavior that you might think is a very small version of this window that I said that Patrick was able to open very wide by going to high spatial dimensions. For instance, you start to see chi4 growing before you see any hint of Stokes Einstein violation. Right? So it looks like there's some separation between one metric of dynamic heterogeneity, this is the growing dynamical length scale, and another which is related to this local, spatially local dynamics. And I think that's very interesting. Okay? So if you buy all of that, then you say, oh, it's great. We know what the right mean field theory is. It's just this. So the answer is no, this is not. Life would be really easy if this were true. But you could come back and just say, well, what happens if I solve this equation in higher space dimension? Because I have a wave vector, and here this is an integration over k. So I can do that in 3 dimensions. I could just solve the equations on a computer in 2 dimensions, 3 dimensions, 4 dimensions, 5 dimensions. And you start to see something that's really puzzling. So just some historical context also. In 1987, Kirkpatrick and Wolonis said in a paper, this equation is exact in infinite dimensions. But they didn't. They offered no proof that this is true. And so Miyazaki on one hand and Schilling on another hand started to look into this question by just saying, if I put this equation on the computer and I solve it on a grid and I do it in higher and higher dimensions, what do I get? And you start to get more and more ridiculous answers. So for example, if you look at dynamical, the equivalent of the Van Hove function, something like the probability distribution things like this, okay, this starts to develop negative regions in high space dimension. But that's ridiculous, right? That's like negative density in the system. So really unphysical things start to happen. And in fact, paradoxically, the behavior of this theory seems to be better in 3 dimensions than it is in 184 dimensions. Right? Things like the behavior of the plateau, and there's a version of this for the self-intermediate scattering function, which should be a Gaussian, at least to a very good approximation in the mode coupling version of it, and that's observed in in computer simulations, but in But in the solutions of this equation, it starts to become like a step function with weird properties. So something weird is going on in the theory in high space dimensions. So on the one hand, qualitatively, you have all of this behavior that looks like you would want to think is, just the detailed version of what you expect here. And maybe you should say that that's still true for a reason I'll come to in 2 minutes. But on the other hand, there's something wrong in the details, because you find when you look at quantities in detail, they become nonsensical. And actually, one possibility for this, and now I'm just totally speculating, this is related to conversations I've had with some of the people in the room, and this could be totally wrong, is if you think about what these theories are doing, they do something that might be correctable. But in the form that they are given here, there's a problem. So if you ask the question, for example, does mode coupling theory, just for a simple problem, a non-glassy problem, does it get the regular Stokes Einstein relation right if I take a very large sphere and I embed it in a fluid? Right? So the Stokes Einstein relationship says that the viscosity would be something like kT over something times the size of the sphere, and the diffusion constant is somewhere, right? D? Or D down here, yeah. And depending on the boundary conditions at the surface of the sphere, you should either get a 4 pi or a 6 pi, whether you have stick or slip boundary conditions. So when you do this calculation a la this guy in mode coupling theory, you get 5 pi. So you don't get 6 pi and you don't get 4 pi. You get 5 pi, which is kind of funny. And that was confusing. But it seemed, okay, it's pretty good. It kind of averages the two. It was Madden and Masters in the early 80s who figured out what this means. So if you look, everything here is done in K-space. Right? If you go back and ask what's happening in real space, what's happening when you make the kinds of factorization approximations that I told you about here, right? What the factorization approximations do is they restrict the wave vectors that you are looking at so that everything is really diagonal in 1K. Okay, so you pair a density mode at K and a density mode at K prime, and that is a delta KK prime. Okay, and if you go back in real space and look at what's happening in the Stokes Einstein problem, what's happening is the boundary condition that you're solving, or the G of R, the effective G of R that you're using, is just one that's flat everywhere. So it's one even at particles on top of each other. And then if you go to Landau and Lifshitz and ask what is the Stokes Einstein relationship for a fluid particle immersed in a fluid, one where the particles can actually go inside the object, the answer is 5 pi. So that actually, the people that did that calculation got the right answer for the wrong problem. Right? They wanted the regular Stokes Einstein with a excluding large sphere, and what they computed was really correct for a problem where you've got a fluid drop inside a fluid. Okay? So it would seem that this kind of factorization approximation is, in some sense, and this, of course, may be related to what I had mentioned 5 minutes ago, that dealing with the real space contact properties is really important. And that in some sense, perhaps when you do the gross approximations that we weren't understanding when we did them here, we are making a mess in the same way that the Stokes-Einstein problem is made a mess. Okay, and that if you didn't make, or if you delayed this factorization approximation so that you didn't sort of diagonalize in K your memory function, maybe you would start to build back in aspects of the exclusion of spheres, which are all important. I mean, this is where everything is happening in higher space dimension. It's all at contact between two spheres, which I think Francesco will mention tomorrow. Okay, so that's just a speculation, which is worth following up on. Okay, so then the question is, there's one other thing I didn't mention, but I want to mention. So I mentioned all of these systems where you can do simulations, and in either higher spatial dimensions or using this Gaussian core model. And one other thing that actually happens is, remember I told you that if you take your Lennard-Jones simulation, well, actually I didn't tell you this. If you solve this equation with input from static structure like S of k and so on, you actually find a transition that not only is too high compared to all the interesting things, but one that actually occurs right basically where glassy behavior starts. So this is a little bit confusing, but when people do this fit, let's say they take the intermediate scattering function and they fit this form, they find that the TC is, let's say the glass behavior in the Lennard-Jones system starts at temperature 1. They find that the TC is fit to something like 0.45, right? That's where the power law fit says. But that's by a fit. It has nothing to do with a theory. It's just taking motivation from a theory and fitting the TC. If I instead, ab initio, solve the equations with real input, I find that the transition occurs at something like temperature 1. Right? So there's a discordant aspect of where that transition is compared to where it should be by fitting the simulation. What you actually find if you go to models like this is that the TC, without fudging anything, starts to correspond more and more to where the fit TC is. So that's another piece of, or indication that higher space dimension is revealing the mean field character, but somehow, as I've mentioned, there's something not quite right about this. One other thing that I wanted to say is that's not such a bad thing from the standpoint of these models. There's like an infinite number of these kinds of models. They all have the same gross phenomenology, right? They all have the gross phenomenology that there's a high temperature phase where the system is ergodic and the free energy is trivial, right? Then there is a dynamical transition where the order parameter jumps and the configurational entropy jumps, but there's no thermodynamic signature, let's say, in the total entropy or something like this. And then you continue to go down in temperature, and basically you run out of these clusters, and the system basically is stuck in an ideal glass state. Right? There are ones for even which the dynamical equations don't look like this. They might look like something totally different, but they have those properties. So there is no reason in retrospect to think that this is a real problem. Okay? It's actually quite nice that the features that we see in a real simulation in higher space dimensions qualitatively agree with what we expect. But we should not expect that in details it should be exactly the equation we get from the p=3 p-spin model. Okay? Yes?
Well, but, so we've been told here that the behavior you get from the is correct for a liquid in dimension.
Well, have you been told that? I guess that's not a precise statement, but I would say I disagree with that. What I would say is the properties of the infinite dimensional solution share all the important properties with the p=3 spin glass model. But that's different than what you just said. And I don't know if other people would agree with me or agree with you, but that's what I would say. I would say that the infinite dimensional solution that Francesco will talk about and the dynamical version of that I'll spend 5 minutes on in 5 minutes share all those properties. That is, they're one-step replica, symmetry breaking. But for example, as far as I understand, in this very simple p-spin model, there's no Gardner transition, for example. But there are other versions of models like this where there is a Gardner transition. So it's not a precise statement. What I would say is that the precise statement is that the infinite dimensional solution of hard spheres, for example, shares all of the important properties as this model. But in the details, there are many models like this that it also shares important properties with, and they differ from each other in specifics that are not important. Is that? Any other questions? Yes? What does correct mean in that context? I don't know. I feel like I mean, I wouldn't, again, I would say that's not a precise statement, and it's one that I wouldn't 100% agree with. I would say that it produces features that seem to be associated with correct features of mean field behavior of systems in the supercooled regime. Whether or not even those behaviors are really there in a isolatable, identifiable way in 3 dimensions is unclear. That is, you see this gross phenomenology, but as I said, if I fit an Arrhenius function to a power law, I get a nice power law. I think Sid's done lots of fits like that. They're very interesting. And so you don't really know. All that we can say is if I want to do a computer experiment that real experimentalists can't do, so this is one reason why we can be proud, right, as simulators or theorists, and Mark Edgar can't do it and Sid can't do it, is I can simulate a system on the computer in 4, 5, 6, 7, 8 dimensions. And I start to see in a more and more convincing way lots of the qualitative behavior and even some of the quantitative behavior I would get out of this equation. But the equation can't be quite the right one, because if I solve the same equation in those same high spatial dimensions, I get nonsense for something. So there must be some equation that's not quite this equation, but it has all the properties of this equation that is right. And that's what I'll mention now. Mm-hmm.
A way of producing like activated continuum fluid mechanics.
Yeah, I think this is really an interesting question, and it's something that many people are trying to do. I think it's one of the hardest, and from the theory standpoint, it's one of the hardest things to do in the glass field, but it's also one of the most important things to do. So there are lots of ways you could try. I would say none of those attempts have been completely successful. So there are phenomenological things you can try, like I could just take this equation and adjust it by a hopping time or something like that, but that's not what you want to do, right? So you can get whatever you want when you do that. You could, do something that several people have tried, where you don't make the approximation that I made here, but I try to continue. I make a memory function for the memory function, sort of a continued fraction, and then and you can get something out of that. But of course, this is like trying to get, in field theory, the activated processes are always the ones that you can't get, right? These are like the instanton processes that are exponentially hard to get by just being smart and picking out the right diagrams. You can't do it. So if you want to try to do it by brute force this way, it's probably not going to be something that you should spend all that much time on. But you could try. For instance, what I was saying before about the Stokes Einstein relation. Maybe you can get a lot more if you just didn't make an approximation that picked out one diagonal wave vector, because, So there are a lot of things that one can try, but I think the answer is yes, people are trying, but no, there's not a convincing version of that. And then you can also make models and appeal to those models. So for example, even if and I think Leticia mentioned this, if I take versions of models like this in finite n and I simulate them on the computer, you will have some process that you might want to call an activated process, which scales exponentially with n. But if you make n small enough, you will kill all of this mean field behavior, and you'll see what you might want to call activated processes. Of course, these are not quite the right activated processes, because they're mean field on the very smallest length scales, and they're just cut off by the size. But actually, that's a fruitful thing to try to do also. Okay, so we could now ask the question, is there a uniquely correct solution, let's say, for hard spheres in d equals infinity for the dynamics? And the answer is yes. And this is, I'm just going to give you the reference and tell you what the properties are. I'm not even going to write the equations down. And I think Francesco is going to talk about aspects that are useful in finding this solution, but not at all about this solution. Is that right? Yes. So you won't see the equation unless you go and look the paper up. Okay, so the reference to the solution is And actually, I didn't write down the full reference. I have the abbreviated reference, meaning the journal and the year. But I think there's only one paper that this could be, and it's 2016. Okay, so what they were able to do is actually solve the dynamics for, I think, for the self-particle motion exactly in infinite dimensions. And it makes use of some of the notions that I told you about. And in particular, you do something like a dynamical virial expansion, and you use the fact that in infinite dimensions, the clusters just break up into pair collisions. Okay, and that allows you to solve the equations exactly. So only two terms survive in the virial expansion in high space dimension, and so you get this very, very nice solution. The solution has the following properties. And I think Francesco will correct me if I'm wrong. I think there is, a behavior like this. So there is a MCT-like power law behavior with a critical temperature. The critical temperature corresponds exactly to what you would expect the dynamical transition is in infinite space dimensions. By the way, that I think is another problem with the equation that I wrote. If you solve the full MCT equations in higher and higher space dimensions, you don't find consistency between the replica approach and the equations. But here you do. So you can, in that language, you can call this the dynamical transition. And you also see other properties. You have sort of these kinds of power law behaviors. You have a plateau that appears in the theory. You also see there is sort of a weak version of the violation of the Stokes Einstein relation. And you see this often in simulations. So even when you simulate in high space dimension or you simulate the Gaussian core model, there is this sort of weird slight, if you take diffusion constant times relaxation time, and that's equal to relaxation time to some power, there is some vestigial, very, very small violation of the Stokes Einstein relation. And actually, that's also true in the plain old MCT that we derived. We spent 2 days deriving. That is, it's not entirely zero, but it's very, very small compared to what you see in the real system. And actually, you get an explicit form from this solution which agrees with that there is some sort of weak, strange kind of violation of Stokes Einstein, but it's much smaller than what you would expect in 3 dimensions. And as I said, this is really nice because it's also fully consistent with what Francesco is going to tell you about tomorrow. And so now, everything is good in mean field land. We sort of know that. And also, if you ask, do the equations look like mode coupling theory? They sort of have some of those features, but they don't quite look the same. So I encourage you to look the paper up. Even if you don't follow the derivation, you can see the degree to which it does look like the MCT we derived and the degree to which it doesn't look like the MCT that we derived. And I think that's really interesting. So now we have sort of a consistent framework where we have a dynamical and a static solution in infinite dimensions, which you could say is the unique mean field theory for hard spheres in infinite space dimension. If you ask, however, and this is again funny, and I don't know how useful it is, how well does this theory work in 3 dimensions? It's actually a lot, I would presume it's a lot worse than the MCT that we derived. I would expect that if there is a collective version, that the plateau, because it's like this in replicas, right? The plateau will look worse. Some of the detailed properties that you could fit to a real simulation would look worse. But that doesn't matter, right? From the conceptual standpoint, that's not what we're really after. We want a consistent picture. So in this sort of framework, we can say that the entire mean field enterprise makes some sense. That it's not just that mode coupling theory in this mean field perspective is, or in the non-mean field perspective, is just wrong. It's that it's supposed to be wrong. That is, it's supposed to only capture the behavior of systems which this is a proxy for in the ergodic phase where the free energy is trivial. And then there should be something in the mean field limit like a strict dynamical transition, and then other things would happen if you go out of mean field below that. So it at least gives you a nice framework for going beyond mean field theory, or thinking about things beyond mean field theory. And some of those things may or may not really survive in low space dimensions that are not related to this dynamical transition, but let's say the Gardner transition. So let's say for hard spheres, it, I think, is compelling and reasonable to believe that it's not accidental that jamming exponents, for example, which are not related to the dynamical phenomena that we're talking about, are correctly quantitatively described by the framework that this all fits into. Okay? So if there are questions, ask them, and what I'm going to go on for the last half hour is to discuss chi4 from the standpoint of liquid state mode coupling theory. So are there questions? Okay. So now what I want to ask is, one of the things I told you is that in these kinds of models, while there is nothing like a local activated process in the mean field when you have a fully connected model, so that what that translates into in the real world is there's nothing like Stokes Einstein or real Stokes Einstein violation or growing non-Gaussian parameters, or if you just look at simulations, there's nothing like these really interesting, or it's not obvious that there's anything like these really interesting bursts of motion, local bursts of motion. There is in these models a growing chi4 that actually diverges at the dynamical transition. So there is some growing spatial extent of correlation in the dynamics. And as I said, if you simulate the Gaussian core model, you can actually see that the dynamical behavior in real space of the particles looks different than what your eye is drawn to in the Lennard-Jones simulations. Okay? For example, it looks like the motion of the, if we define things, if we define things like we can, or I'll call this, well, yeah, fine. I can look at something like, let's call it S. I don't know, I'll just call it A. All right, so if I can look at something that should be like the structure factor. Right, and just like I would near a critical point, I'll see, and this, let's say, I'll see an upturn in the behavior at low k, which is related to a growing dynamical length scale in the system. So again, remember, and you've heard this numerous times, if you just look at the static structure, S of k, I think Gilles beat into your head too much, nothing happens in S of k. It's true that nothing indicative of any growing length scale happens in S of k. This is for sure, because the static density and even the dynamical density field is not the right order parameter to look for. Of course, S of k does change as you supercool the system. That was one of the things I told you why in the MCT equations you actually get something, because even though it changes in a way that it doesn't look interesting by eye, it's enough for a nonlinear equation to give you a glass transition. But here, this order parameter is 2 space and 2 time. So this is like the Edwards-Anderson order parameter or something like this. This is like the dynamical plateau order parameter, and there is a growing length scale, and this will change over supercooling, and you can extract this length scale from a quantity like this, and you will see growth. Okay, and by proxy in these models, there is also a growing length scale of the same type. Of course, there's no spatial dependence here, but the Q or k equals 0 version of this guy, which is the chi4, if calculated properly, also grows and actually diverges at the dynamical transition. Okay, So the question is there a way within liquid state mode coupling theory to actually calculate this? So one thing you could try is you can write this down in terms of density fields. So this is actually also going to be proportional to, you know, with some Fourier transform of the step function in there and so on, right? It looks like pairs of density modes because I can Fourier. Anytime I have a difference in space, I can always do the same trick I did for the force, right? And then this is going to look like a 4-point density correlation function minus the square of fkt, something like that. This is really hard to do. There is a paper by Bouchot and Baroli, or Baroli and Bouchot, not to be confused with the Bouchot-Baroli paper that was probably discussed last week a lot in 2004. And I think it's 2004, and it's in EPL, which sort of does this by brute force. It does sort of the 4-point correlation function. And actually, it's a very interesting calculation if you know something about superconductivity, because basically what you sum is all the ladder diagrams for the 4-point function, and the divergence of chi4 is related to the soft mode, which is the divergence in the denominator of summing the ladder diagrams. So that's the way this calculation works. But it's impossible to do this calculation in a way that fully satisfies liquid state people. So there's some schematic aspect to it. And so what I'll tell you about for the last 20 minutes is how you might get, you know, from the confines of the full MCT that we discussed, how you would get some information about what this growing length scale is and what the predictions are. But the calculation is tedious, and I mean, it took us 2 days to go through just FKT. So it would take us 4 lectures to go through the version of that for higher point correlation functions. Okay, so how do we do the calculation? So instead of, so you know from critical phenomena, you could look at the fluctuations in equilibrium of the order parameter, and that gives you a susceptibility. And the susceptibility should be telling you something about diverging length scales near, let's say, the ferromagnetic transition. Or instead, what you can do is put a field on the system, right, and measure the response to the field in the limit where the field is going to 0. Okay? This is what we are going to do in the liquid state case. This is much easier to do. So what we're going to do is, and this paper is in here, and we had always thought it would be a good idea to write a long version of the paper where all the details were, and we had many drafts of it, and then Jean-Philippe sort of left physics to make lots of money, and then we never wrote it. So if you're interested, I might have it somewhere if you ever want to torture yourself and try to go through all the details of the calculation. I have notes for you somewhere, but I may not answer the email. If I don't answer the email, it means I don't have the notes. They were like 4 laptops ago, and they're nowhere to be found. But you can get the idea from the paper. So the basic idea is I'm going to put an external field that could be spatially varying across the system. Okay, so there is some length scale associated with the spatial variation. It could be like cosine, right, kx or something like that. So there's a length scale induced by the field to begin with. Okay, and then I'm going to measure the fact that this is a spatially modulated field means that, strictly speaking, I'm breaking the space translational invariance. So this would be something like okay, and K1 plus K2 plus the Q of the field have to add up to 0. And by the way, the calculation itself is interesting because for more exoteric uses, you know, for instance, if you wanted to calculate the response of a supercooled liquid to a spatial inhomogeneity like a wall, this approach should be a useful starting point to do that. Okay, so that's what we're going to do. And then we're going to define a susceptibility, which actually turns out to be just related to a 3-point function. Oh, so first I should write down what does the mode coupling equation look like for this guy. And I'm not going to write down what the memory function looks like, but it almost looks exactly like what you would expect from what we've already derived. Right, so that's exactly this form, but it's for the matrix of wave vectors for the dynamical structure factor or the self-intermediate scattering function. And at this stage, pretty much everything that goes into this memory function is sort of k minus k prime versions of the same thing integrated over, this should be prime. Right, so it has that form. Okay, then we're going to define a dynamical susceptibility. Which I just take the variations of this, and I just want to write it out in the same way that we did for so I'll define this as okay, so basically what I'm measuring is the susceptibility or compressibility of the dynamics with respect to a field in the limit where the field goes to 0. So by some analogy with critical phenomena, this should also tell me about a growing length scale. You could rightly ask the question, well, so what? What does that have to do with chi4? Maybe that has no relationship to the chi4 that we all learned about here in the last 2 weeks. And the answer is there are theoretical reasons, some of them written down in a paper that Ludovic and I and Walter Kobe and Miyazaki and Bouchot and Baroli wrote down in 2007, so it's 10 years old. But those were sketchy arguments. Another thing you can do is just simulate this, right? And this is something that that we've actually done. I have a reference if you're interested in a relatively recent paper. Actually, I didn't write it down. Oh yeah, I did. So there's a non-equilibrium computer simulation you can do where you do the simulation in the field and you ask the same question, and it looks like the results are fully consistent with what you would get from the equilibrium calculations for chi4. Right, and this is Journal of Physical Chemistry, B, 2013. So again, the idea of the simulation is to take your favorite mixture, put the field on, do the simulation in the field, make the field weaker and weaker, and extract the susceptibility from the field and try to extract information about the behavior. And it's a little bit hard to be really sure, but it really, at least it looks semi-quantitatively like it's what you would expect exactly from just measuring chi4. So this susceptibility is what we want to calculate, and we can do that, right? I mean, it's a big mess, but we have this this matrix dynamical the intermediate scattering function, and these quantities will depend on the field in ways that I haven't written. And I can take the derivative with respect to the field, set the field to 0, and collect everything. Okay? So I'll write down, this is the last real equation that I'll write, but I'll write down what this susceptibilities equation looks like, because it's not that informative, but we still have 15 minutes, so I can torture you for 15 more minutes. So it has a mode coupling-like equation. So all of this just looks like regular MCT, and M0 is the MCT memory function. And then you got a bunch of other terms. These V vertices, I'm not going to write down what they are, but they also just depend on things like S of k in the field free limit. This is all under the integral, so times and this S is not a structure factor. It's a source term whose form is not important. So instead of equaling 0, it equals some function of k and q, which could just be like a Gaussian function. It looks horrible, right? I see people laughing at the front of the room. So it is horrible. But there are some recognizable terms. So this part looks like the MCT equation for F, but it's for chi. Okay? Then all this other stuff comes from the actual explicit U derivative. But all of these guys also depend on things like the direct correlation function, which, if you remember, is 1 over the density times 1 over 1 minus 1 over S. Okay, so, and this is the regular structure, the intermediate scattering function. So this is an MCT-like term that's multiplied by all this. So we've got F, F, and chi. So there's a nonlinearity, and this is how you know it's a sort of a 3-point function. If you wanted to work out what this is, it is a 3-point function. And if you want to read more about those, the 2007 paper that I mentioned with Ludovic talks a little bit about this if you read between the lines. And then you can solve these equations, or you can make a schematic form like we did for the regular MCT equation and ask, what properties do you get from these solutions? So this allows you to get really detailed information about what you expect to be the growing length scale associated with chi4. And checks like this one should give you some confidence that they are really telling you about the same length scale as what's in chi4. And so I'm going to, in the last 5 minutes, just tell you what those properties are. Damn it, I did it again. This is worst board technique ever. As I mentioned to you on the first day, the problem is at Columbia, we don't have any blackboard systems that were invented after 1930. So there's never like multiple boards, 3 boards. We just have like 1 board and like an old eraser from 1950. And so when I teach, I'm never tasked with such a challenge to actually use the boards. So these are the properties that come out of the solution of this dynamic susceptibility. So there is a growing length scale. And it diverges in the following way. So the exponent is 1/4. There is a space-time scaling between length and time scales. Okay, so remember what gamma was? Gamma was the way that the 2-point function, the exponent for the divergence of the 2-point function. I said it was 1/2a plus 1/2b. So if you ask what are the values of a and b in the Leonard-Jones, gamma works out to be something a little bit greater than 2. Let's say 2.5. So actually this z exponent is enormous. Right? 4 times 2.5 is something like 10. So it's like relaxation time goes like length to the 10. This means that length scales are growing incredibly slowly. Okay, but they still eventually diverge at the dynamical transition. And also there's an interesting thing that there's a growing length. So there's already a growing length scale in the beta relaxation regime in the theory. So the beta relaxation regime is not something stupid, right? You know, in the old days when people did simulations, they just had a plateau and they said, oh, that's just local uncorrelated behavior. But it's not true. Cages have some correlation that's spatial and it's growing. Okay? So already in the beta regime, there's a growing length scale. By the way, this has been confirmed by a lot of people, but there is a recent PRL by Sastry. I have the reference here. I'll write it down. But Karmakar, Dasgupta, and Sastry from last year, which makes this explicit and extracts the length just by looking in the beta regime. So this is a prediction of the theory. It's correct. And also one other thing that's interesting is the scaling form in the beta regime and the alpha regime are different in the theory. And what this implies is you can calculate from this what it means for the fractal dimension of the correlated regions. If you wanted to think somehow you could say something about real space, what it says is that in the beta regime, dynamical heterogeneity is sort of extended, and in the alpha regime, it's compact. And actually, this is observed, obviously, in simulations, right? You see sort of stringy-like things in early times, and you see more compact things in later times, or at least confirmed maybe is too strong a word. Again, there is some degree of this, I'm getting the result that I want by looking for things in a certain way, but there is some evidence that there is a difference in the geometrical structure of the dynamical heterogeneity in the early times that is more fractal-like, and in late times is basically space dimension-like. It's compact. Okay? So the last two things, I won't write that down, but the last two predictions have real support in simulation. There was a period of like 2 months where we were in contact with Hans Andersen, and it looked like these results were quantitatively accurate, which made us exceedingly happy. But of course, we knew better, right? This is a mean field theory, and I mean, you don't expect the exponents in your mean field theory to be right. But somehow it seemed like without him knowing what our predictions were, he was getting exactly 1/4 and exactly, you know, this space-time scaling. And we thought, wow, that's great. You know, we made a real prediction. It turns out it's very subtle, and maybe Ludovic talked about this. Trying to extract the well, I erased it, but trying to extract the properties of the length scale in a real simulation are very hard to do. You have to be very careful. And Hans was using 27,000 particle simulations. So you can get down to some limiting wave vector, but you can't get as low as you want. And then it looked like all of this is right. And then Dasgupta, Karmakar, and Sastry came along, and they did like 300,000 particle simulations, and these are not right. I mean, they're qualitatively right, but it's more like what you would expect. It's more like if you wanted to even fit it to a power law, it's more like this is a half, and so on. So qualitatively, this behavior is right. And qualitatively, in particular, that the fact that the beta regime is already correlated and that there's a change in geometry of dynamical heterogeneity and going from the beta regime to the alpha regime is more or less right. These things are qualitatively right, but not quantitatively right. One thing that would be super interesting to do, but as far as I know it hasn't been done, is to take either your favorite, Patrick 8-dimensional simulation, or just go to the Gaussian core model in 3 dimensions and ask whether this is more right. Again, those models are much closer to mean field theory in the sense that I described, and maybe this becomes quantitative. As I already mentioned to you before, if you simulate chi4 in the Gaussian core model, the peak grows much more like what you would expect from this. That is, you can just get the scaling of the peak height, and it's much more like what you would expect from taking the length squared, and so it has more of this behavior, but not quantitatively. We don't really know if this is the case. So that's one really interesting thing to try. Another really interesting thing to try would be to ask, well, this is all good and well, but I already told you that my liquid state MCT isn't quite right. Is there a d equals infinity version of doing this calculation? Presumably, there is a way to calculate chi4 in d equals infinity because it's like the p-spin model, but I don't know if it's been done or if it's hard to do. That would be another thing that would be really nice to work out. So that's pretty much all. One thing that I wanted to say is, as I told you, I skipped over one large chunk of the notes, which had nothing to do with glasses. It was just after we had gone through all of the memory function and Morey-Zwanzig stuff, I wanted to show you that that approach is more general than just looking at things like liquids. And so the problem that I worked out is just an electron moving in a polar medium, the polaron problem, and working out the mobility. And what I said was you find the solution by Morey-Zwanzig plus mode coupling, which is identical to Feynman's solution and very similar to Kadanoff's solution, and those were obtained by much more complicated means, either double path integrals or Boltzmann equation. And in my notes, it's pretty detailed, and it's not that hard, and you get a very nice solution. So if you care, just go through that, but I won't have time to do it. And that sort of draws to a conclusion the lectures, all the stuff that I have to tell you. So that's it, and I'd be happy to take any questions. People have been beaten down by, yes?
For these coupling type equations, like you have to worry about uniqueness and all.
Oh, for solving this equation? We didn't worry about uniqueness. Presumably, you should worry about uniqueness. The actual 2-point function we know has a unique non-trivial solution. This has been proven. Nothing has been proven about this equation. Sid?
So I just want to make one comment. I'll try to talk a little bit about some things in my lecture. But you talked about divergence in non-linear accessibility, and saying that there is no, essentially, assuming there is nothing in the linear accessibility, but experiments seem to indicate that there is something in the linear accessibility.
Yes. Yes, so that's a good comment. So I made the mistake that Gilles may have made where I spoke too broadly. So this is a good point. I mean, there's nothing within this framework that would say that there's something in the linear susceptibility, or maybe there is, I don't know. But yes, that's true. There's certainly nothing in S of k that looks like a low Q interfacial behavior. Yes? Yeah. So if you read the paper, This paper, not this paper, the 2006 PRL with Bouchot, Baroli, Miyazaki, we discussed this. So there is a gradient expansion way of understanding this equation as well. So at the end of the paper, this is discussed explicitly. I think there's like a 5% chance that I have all the explicit notes because I can't remember actually how that worked. This was like 11 years ago, and we didn't follow up on that. But I might be able to find it. If you ask, I can send you more details. But if not, at least there's a paragraph at the end of the paper that goes into exactly this issue. All right, let's get coffee.